in that sense, we can't really have something meaningful. But I want to do two things. May not take an hour and a half. And we have no chalk and a lot of markers, right? We have chalk now. Good. So I'm gonna leave the maybe projector on. Maybe I should turn it off. Okay, so first, I want to talk about logistics really quick. One thing that we need to address is homework 6. I think most people have no problem on homework on problem 1. Most people will not try the Netflix data set right now, but they may try it after the course is done. I think that's an interesting idea. In particular, if you do that, the interesting approaches about Netflix, I can give you some pointers for how to try that. The most interesting ones are the ones that use more than just the Netflix data. Netflix data comes in a basic matrix like users versus items with rating matrix. But the people who were really successful at it, we talked about it at office hours a little bit with a few of you who came. They scrapped those movies information from other websites like IMDb or Rotten Tomatoes or things like that, and they managed to have a combined approach, content and ratings. And the hidden layer, if you like, or the equivalent of, say, topic modeling or something, that the concepts that are being discovered in the data, and here are those user profiles. If I want to know how a user reacts, I could look at its rating matrix or ratings vector, but it's much better to build a user profile in terms of what kind of things this user likes in general, not in particular for a movie. So those are complicated things that have been studied a lot because Netflix put up this prize, $1 million for whoever improves their recommendation algorithm. And at that time, there were a lot of recommendation papers. Okay. So then we need to talk a little bit about the problem with the social graph mining. We have an exam. That is for, 25th? Is that a week from today? We say 12 p.m. So you need a computer, charger, etc. So 12 to 6 p.m. And I would say you want to have software ready. Not just install. I mean software that we've been using, things like Elasticsearch, TensorFlow, NumPy library, Scikit-learn, right? So you don't want to spend the time during the exam figure out how to install Python libraries. The ones that we've been using across the class, PCA, EM, so I expect that those are already ready and installed on your computer. So, and you already know how to call those. You don't have syntax problems because presumably you've been using them during the course.
So the Elasticsearch trial that they gave us, that was only Elasticsearch trial that we had from the link, that was for only 14 days. So we don't.
What? I can't hear you.
The Elasticsearch trial, our website that we signed up for, they only gave us the trial for 14 days.
For Elasticsearch?
Yeah,
I think Elasticsearch is free.
We tried from different other platforms, but like we want to use their Kibana and everything that was there.
Is that true? I've been using Elasticsearch and Kibana or at least 3 computers, and I never paid a thing for months.
Yeah, it's free. You need to pay if you need support or something.
Yeah, that's what I will look into it, of course. My understanding is Elasticsearch is free. I've installed it on at least 3 computers myself, using it, and I never paid any support, but I never have a problem of expiring in 14 days.
If you're hosting on the cloud, then it is. If you're hosting on local, then
I mean locally, I always hosted locally. So I would assume that you can design a complicated setup. Somebody asked me yesterday, my setup is on a computer at home, on a server at home. Can I SSH in my computer at home and do my work there? Yes. If you have a setup, Amazon server or something, you know, or some environment somewhere else that you can use, you can do that. I think it's harder. I can't promise you the SSH connection is gonna work that well. But as long as you don't collaborate specifically with other people, so you are, during the exam, you can search Google, you can check up what other people have done, things like forums, and even copy paste some code if you'd like. But you cannot collaborate by asking specific questions to specific people, either in this class or outside the class. So you can't have your friend on standby. Maybe I'll ask you some questions during the exam. But your computing environment is totally up to you. Most people will bring their laptop, other people will SSH into a computer they have. That's fine. I can look into it, but I don't think that's true. I think you can set up Elasticsearch locally and just use it. There will be two problems that will take 1 hour each, plus some thinking, plus some trials. So my approach for this exam is that each problem, once you know what you want to do, it will take about 1 hour to do the whole problem, including write up what you've done. At the end, you have to say, this is what I've done in a bullet form, not a formal report, but a bullet form. So class report. And you have 6 hours for 2 problems. That is, each problem may take a trial and error approach for a while and some thinking and some Googling. And then you will decide, okay, this is what I'm going to do. I'm going to extract hard features from those images. I'm going to do this and that. The moment you have your approach, I think it will take about an hour to do it. It will not be computationally intensive. So I do not plan to have a data set that you're going to wait for your computer for 20 minutes to run it. There's going to be running algorithms, things like k-means could be. I would assume a decent implementation of k-means, if you have to run it on a problem, will take about 5 to 8 minutes max. Okay, so I do not want to waste the exam time on waiting because the data set is so large. But there will be some runtime, so you have to bring your charger because you may run out of power. Who knows? I think that's it. We might ask questions after the exam for grading. So it may be that I do not plan to have demos for everybody to show me what they've done, but it may be that for some people, me and the TAs will look at what you've done and we would not understand how that works or why it works or what you mean. In that case, we'll find a way to talk to you. If you left the country, nevertheless, we'll find a way to talk to you, but you have to be available. So if you booked your plane ticket on Wednesday night, that's fine if we can get a hold of you on Skype, for example, Thursday or Friday. Okay? So we might have to ask you, I see your code and I see your report, and why did you do this, or how did this work, or what parameter did you use when you run this and that. The report might include a plot. So if they do, there might be a simple thing. For example, plot, I don't know, number of features versus number of clusters. Now, I make this up right now. This is not related necessarily to the exam. So then you might have some line or some plot in here, some bars, I don't know, something like this. So if I ask for a plot, it'll be something simple, but make sure you know how to create a plot. Like you can use your favorite R, Python, MATLAB, Java, anything that can create a simple plot, either a dotted plot or a line plot or something. You should have that ability. You don't have to do it in the same language that you do the program. So I know plotting in MATLAB very well. What I do if I run Python or Perl, I dump a file with data, like 2 columns or 3 columns of numbers. I load it back in MATLAB and I plot it. If you do that, that's perfectly fine. But you really want to know to have software ready. So you don't want to spend an hour installing MATLAB during the exam. If your favorite plotting system is MATLAB like me, you want to have MATLAB ready to just create plots with it and know how to call the plot command. Okay?
So Professor, so the exam is going to be more focused on implementing some of these algorithms or calling these libraries or what it is?
I don't fully decided yet. Again, I'm targeting about 1 hour. So I'm expecting that if I say something completely new, which is probably not going to happen. I do not expect to ask you during the exam to look at some algorithm that you haven't seen, unless it's something extremely simple. I much rather expect to say run PCA or run EM, and I'm assuming you have the code for that homework. So that may be a problem if I don't have the code for PCA in homework 3 and I'm required to implement PCA. What do I do? I'm not saying that's going to happen. Maybe I'll just say run a package, but I'm assuming you have access to your code from the previous homework. So I plan both problems to be related to what you've done. Very likely the problem is going to be like, here's an algorithm that we have in homework 2, KNN classification. I'm trying this on this data set, bunch of images. I notice it doesn't work because something. What should I do? And maybe I have 3 options. I could extract new features, I could increase the KNN parameters, I could run some different clustering algorithm first and record the clusters ID and then change KNN to do something. So I think in most cases the main algorithm, something a downstream task like KNN, it's something either very easy to implement or something that you've done already or something that you can call a library for. But then the main thing on each problem is going to be, since this doesn't work the way I expect, what should I do? And the report will ask you to explain why that works. So since it didn't work in the first case, but now that I've, say, extracted new features or sampled the data or kick out some data points or something, well, why is now working? So I don't think there'll be significant time sitting down with a piece of pseudocode, how do I implement this algorithm? That's not a main task in this example. Yes?
Are we restricted to use algorithm that's only taught in the class? Or
That's going to be specified. If it says specifically use some algorithm, you have to use that one. So if I say use PCA, you have to use PCA. And further, we're going to specify whether you have to use your own PCA or some library.
No, so if it's an open-ended algorithm, say solve this problem in the best way.
It won't be like that.
Okay.
That I think will take, I mean, if I ask that, okay, I don't want to promise. If I ask something like that, then I'm going to let you use whatever library.
No, not only libraries. So do we have to restrict ourselves to the algorithms covered in the class or any other algorithms?
No. If I say something like solve this problem, but it's unlikely to have such a general statement because I think that cannot be done in an hour unless the problem is very simple. So if the issue I have with such a problem, if I put it on, is that it's either something very simple that the first thing you try is going to work, right? Like naive Bayes. Or it's a complicated problem, in each case you're going to need more than 2-3 hours to solve it. So I can't ask an interesting, fancy question on algorithms that you haven't seen. But I may ask a question, here's a data set, perhaps one that you've seen already, 20 news groups, and my task is to cluster documents with a property that clusters are a superset or align as a superset. Suppose 20 news groups has 20 labels, right? Suppose I want 5 clusters, and I want the 5 clusters to supersize the labels. So like every label set to be a part of one of the clusters. So now a cluster may have 3 labels, but I don't want labels spread across the clusters. I may ask, what algorithm should I use out of the clustering algorithms that we've studied? And how should I run it? And run it. So then you have some choice, obviously. We do 2 or 3 clustering algorithms. It's gonna be one of those. I do not expect you to come up with a brand new clustering algorithm. But then, if the problem has a specification, which one should I try? It's totally fine to the exam to try something. This is not a theoretical exam in which you have to decide, and once you decide that you can't change your mind. You can, instead of thinking too hard, try 2 or 3 algorithms and see what happens. Right? Anybody else? Yes.
Yeah, do we need to get like a very high accuracy or something, or should we just?
I think we're gonna specify that, not exact. I'm expecting you to get 80%, but if somebody says I got 65%, I may say that's not enough. Now, let me, in the interest of honesty, let me be honest with you guys. I've never run an exam like that before. Okay, this is the first time. And I think you never have an exam like that before. I think you had coding interviews, maybe, that are very well specified. Here's input, output, test cases, you are required to do this, this, and that. That's not like this, right? In a coding requirement interview, you sit down with Java and you program it, you don't Google anything, you don't ask anybody right there, and you have a very exact specification of the problem. That's not this case. So let me ask a question for you. Can this run into some massive trouble? We imagine the exam going one way, and for some reason it goes the other way.
Tons of questions during the exam, very noisy.
What?
A lot of questions may happen.
We're not gonna ask questions, I mean, to me, or what kind of
To the
questions?
TI or to you, right?
Right, we're gonna allow questions. Questions will be asked loud if you guys want loud. And if I would be in the exam, I would ask question, ask loud. If he has a question and I'm in the exam, I would prefer him to ask the question loud so everybody can have the answer
But
loud.
then it will be very noisy.
I do not expect that we're gonna have a lot of questions, but that's a good point. If somebody's bothered by noise, and some people are not, we can have questions, say, here's a period of questions, for example, I don't know, 20 minutes, and then an hour without questions. So if you have a question during that hour, you have to ask it very quietly in private to me, raise your hand kind of thing, and I come. But again, if I would be in the exam, I would prefer loud questions, assuming they're not questions all the time, because I think we want to mark the answers down maybe on whiteboard so that everybody can see them.
So I think if instructor or professor finds it's a
That's me.
interesting question, so then if that is said loud, I think that is enough, because not all questions would be interesting. It would be more specific to that person.
Sure.
So
So we'll do the thing with time. Will be a time for loud questions, and a time for the rest of the time will be questions just in private. And if somebody asks me a question that I think is extremely relevant in private, I'll write the answer on the board so everybody can see. I do not expect there will be that many questions. So overall, we're talking about 6 hours. A question takes, and an answer on average takes 1.5 minutes, 2 minutes. So if we have 20 questions total, that will be 40 minutes out of 6 hours. I don't think there will be a lot more questions, but let's see. If it comes down to noise and, like people can't work in peace, we'll quiet it down.
should we bring something to eat as well in the 6 hours?
That's up to you. The exam is going to end at 6. Some people might end a lot faster. I'm not trying a very challenging exam here. So I'm not planning for something that is highly intellectual, that requires huge amounts of creativity or a sparkling new algorithm that you haven't seen. So some of you will finish in 2-3 hours. Some will stay longer. That's fine. So if you finish early, you shouldn't feel like, okay, I finished early, there must be something wrong, because how can this finish in just 2 hours? It may quite be if you are a good programmer and you know what you're doing, that this runs. Okay. It also, this exam, as opposed to other courses, either by me or other professors, won't be a high percentage of the grade. Normally exams are about 30% of the grade, and if they have 2 exams, like midterm and final, that may be 60% of the grade. In here, this exam will be maybe 20%, pretty much like a homework, more or less. Maybe a little bit more than a homework, but the exam is not the end of the world.
lectures, but it would be nice to have certain times where you just say what the expected accuracy is.
Yeah, so it's been asked. I'm still solving those problems for the exam. So maybe I'll just say, you meet the minimum of that, just like the TAs did for the homework. I don't decide that. I took the point, you said it, he said it, other people have said it. When do I know I'm done? I'm considering that, but the main part of the grade won't be for the accuracy. Will be whether you try something that's reasonable and you can explain why that works. So before you tried, something didn't work and now it works, or how it works, or why the clusters do not align with the labels using this approach. I'm following the 20 newsgroups example here.
And we said for each run it would take around 8 to 10 minutes, right?
What?
For each run of an algorithm, it would take around 8 to 10 minutes, right? If it takes that, if you keep on changing the parameter, if you need to experiment with like at least 5 parameters, that would alone take almost like an hour for us to just experiment, even though we are completed.
Right.
So-
I would imagine that you would sample the data set to try parameters much faster than that. And
Okay.
only when you decide on a parameter that works, try it on a bigger set.
But that might not scale up to the bigger. If you sample it, it
Right.
might work for the smaller set.
Again, I'm not planning that the computation to be the massive part of the exam.
Right.
So the actual running, I say 5 minutes a run, maybe you do a few runs, maybe it will take 20 minutes, half an hour. I do not want to ask you guys to try a lot of things and then you end up waiting for your computer to do the job. The data sets will be smaller. If I do 20 news groups or MNIST or other data sets, I won't give you all 60,000 images. It'll be a much smaller data set.
What kind of input I will provide or from website?
I think it's going to be the same. Oh, what form? How do you get it? I think that's going to be like a homework, an HTML file that once we're in the class, it becomes available. So again, I'm running this for the first time. I think you're doing it for the first time. I'm aware of doing things for the first time. And I'm not scared of doing things for the first time. Okay? I think it's the right kind of exam to have in this class, so I think we should do that. Would you rather solve math questions with proofs, like many other math data mining classes do? We can look for some proofs in the book. I don't think it's the right exam, and I don't think you guys want to do that anyway. So we'll try something like the homeworks, scaled down to 6 hours. Anybody else?
So is it in place to charge my laptop?
I arranged with the CCIS people. They promised me there will be some power cords so that everyone can have power. Now, would they really have 70 plugs to put laptops in? I think so. If not, we might have to become creative. I don't know if you need to charge all the time. If somebody doesn't need to charge all the time. The plan currently is for everybody to have a power plug. May have to buy some power cords to do that. All right. Homework 6, we said this before. Homework 5, there is no effective deadline to do demo before, what is it, 4/28, something like that. After the exam, they will be allowed to do demos on homework 5 and 6, but no back and forth. Once you show up and say, I want to do the demo, what you have is what you get. There will be no, okay, fix it, come back after the exam. So to do the fixing, come back, you should do that before the exam, because after the exam, we'll be busy with the exam. So that being said, I already said this. How many people did the trace evaluations? Hands up. Please, it will be a favor to me and good for you and good for the next students to do those trace evaluations. Like we said, try to be honest and constructive. But it does look good for me, apart from the actual numbers, if more of you do this trace evaluation. Okay, it is the reports are what is the score, which is what you put, and again, be honest about that. But it's nice to have in a class of 60. Say at least half of the people filling those trace evaluations. And then we have the grades. How many people check their grades already? Hands up, okay. So the system works. You have to check those grades to make sure we have the correct grades for you. At some point next week, there will be other columns in that spreadsheet, like the actual numeric final grade, including the exam and so on and so forth. But for now, just check that you have the proper grades in there. Now that being said, let's talk about something interesting today. What should we talk about? Like I said, this is not a traditional lecture. We talked about quite a few things, right, during this term. A little bit of classification. Some people run regression, I think everybody. I think people run decision tree, TensorFlow. Any other classification? We do KNN. Is there any important classification algorithm that we did not run? I'm asking this specifically for people who are going to take this class, but not machine learning. If you plan to take machine learning or already took machine learning, this is not a relevant question because supervised classification is much more of a problem in machine learning. But if you really want to address supervised classification, which is still, even today, the main machine learning task. Most of the machine learning works by looking at existing data, aka training data, learn a model, a pattern, something, and apply that to future data, or next data, or some other data. Right? Even translation models or face recognition work by annotating first something, who's in this picture, and then learn the models and predict people on future pictures. Right? So supervised machine learning is still the basis of everything in data. Is there any important machine learning algorithms or patterns or things that are being used a lot in practice that we did not do?
Random forest?
Yeah, mostly.
Random forest, let's just say ensemble models. Boosting, random forests. Those are extremely powerful methods, and in some instances they are preferred to neural networks. I know most supervised machine learning, like you also know, it's done now with deep learning networks. But there's good reasons to use such a model as opposed to a deep network. An ensemble model, well, we can't really talk about it. It's the idea that, say I'm adding there's a classifier, right? It's a tree. I'm adding it with another tree, and with another tree. And with another tree. That's what makes it an ensemble. I mean, it's very conceptual. And I'm building those usually greedily. I first train the first tree, I'm not going to change it. Whatever's done is done. I say, how should I train the second tree to help whatever the first one didn't do? What's done is done. Again, I train the first two trees. There are models that go back and say, wait a minute, after I train 4 trees, go back and maybe change this one. But that's complicated. In practice, in industry, most of these models are trained greedily. Do the best you can. Given those 4 trees, how do I train the 5th one? The reason trees are preferred in those models is because trees are very complementary with the idea of addition. To put that in perspective, if I use regression models, what's the obvious problem? If I add 5 regression models,
You're averaging.
what am I going to get?
Giving it a single line.
I'm getting still a regression model. So it's not in an ensemble sense, what would be the point of training 5 regressors, one after the other, and add them up, when addition of linear function is still a linear function? That's only if I believe somehow I can train that overall function to start with. But regression is a global model, it's trained globally, and we know it's convex, right? So why not just train it from the beginning? There's no point training 5 of them. Decision trees are usually preferred for this kind of operation because the way decision trees work, we look exhaustively brute force for the best split with some criteria, right? Remember, at every split, I'm checking all possible features with all possible thresholds to see what's good. That's an expensive operation, but that's very complementary with the notion of addition. This exhaustive search, give me the best you can split. Cannot be replicated with just addition, right? So that's why these two operations are complementary to each other. A lot of ensemble models would use something like trees, typically very short trees. You'll see something called decision stumps that are very short trees because we don't want to increase the complexity this way. Either way, if we increase the tree or increase the ensemble, that increases the complexity. But increasing the complexity that way, it's much better. For example, for overfitting purposes. And if a tree goes down, becomes deeper, it overfits immediately. But in a linear ensemble, it doesn't overfit so fast. Plus, additions. If I want to grow the complexity to this, I can add more trees, or I can make the trees deeper. Addition plays very nice statistically with variance. Right? Do we know that? When we add up a bunch of things, what happened to the variance?
Small.
Becomes smaller and smaller, right, on average. So that's a way of saying if this guy has some errors, and this guy has some errors, and the errors are relatively independent, overall, they might cancel each other, they might complement each other. Very unlikely to have all the errors going in the same direction. In fact, the ensemble main controller will do exactly that, will enforce that the errors don't go in the same direction. So that even if there's an error here and here and here and here, overall those errors do not add up. There's some boosting proofs that do exactly this. So what about the accuracy? If I do this, can I become, we know that if I grow a tree very deep, I get infinitely accurate, right? Because it just learns all the data patterns, everything that's in there, memorize, creates a gigantic table of everything. How about this way? If I grow my ensemble, I'm willing to add a lot of trees. Can I go very accurate? If the trees are short, no tree might be very good in itself. Each tree may have at most 70% accuracy. Can I add them up and get something that's very accurate? Yes, there is a main theorem that got many prizes in computer science that says you can add up weak models and get something extremely accurate. This guy from Princeton who did that. So this is something that if you go and you solve real problems, you should know how it works, not all the math, but the details, and you should have access to an implementation. By now, there's quite a few packages which are very good at implementing boosted decision trees, random forest, gradient boosting, all of that. I think recently there's one from Microsoft that's very fast. It sacrifices a little bit of accuracy when it searches for features, but it's extremely fast. So that's one thing that, independent of what you study during your program, as a data scientist, you should know how to do this.
So how are you going to make decisions? So each and every one predicts one. How are you going to make a final decision?
Oh, it's going to add them up. The model is going to say, call this, give me something. Maybe a probability for each possible label. Then this one does something. It's a score. This one produces a score for each. So I have 20 news groups. For each label, this one produces a score. This one produces a score, a score, a score. Per label, I add the scores. If this tree has no prediction for some label, I put 0 for that one. And then at the end, every label will have a score. There is a different concept here of how to deal with multi-class problems or multi-label problems. Most classifiers are binary, black versus white. But in 20 news groups, I have 20 classes. So there's different wrappers for how you can, say, train 20 different classifiers, pick the argmax or some other ideas. Independent of that, this could be a binary classifier or a multi-class classifier. Okay.
Typically, there are some problems where you can have one or more labels for the same.
Right. So that's good, because that's my next point here. Multi-label problems. That is a data point, it's X, it's X1, X2, up to XD, but its label is Y1, Y2, up to YL. And each one of those things are 0 or 1. So in 20 news groups, if it's a multi-label problem, I have an array of 0 ones. And what he said, I may have more than 2 ones there, because a document may be tagged as business and economics and politics. So how do we solve these problems? This is a hot area in machine learning right now. A lot of research coming in the last 5 years or so, how to do this, or exactly what is the difficulty. Why can't I just train a classifier for each one of these labels separately, right? Binary. And then call each classifier, whoever predicts plus or that label, I put that label on, and whoever does not predict that label, I leave it on, right? So literally, you guys follow me? I predict each one of them separately, and I create a vector by calling 20 classifiers. Why is that not the obvious thing to do? That's one thing. The other thing is how to deal with the problems, multi-label problems at scale. So you're Facebook or Google or YouTube, and you have tags, okay? You have billions of data points. What do you do? So those are hot areas in machine learning right now. Why can't I train the classifiers independently? What's the problem with that? Somebody else?
They are
Maybe because
correlated.
the labels are not.
They are correlated, there's dependencies. So some dependencies, especially the ones you read in academic papers, the one that make the case, are, can I see an animal in a picture, right? And I have to predict what animal is, or the tag. And if I have independent classifiers, I have a classifier for dogs that gives me 80% chance that that's a dog. So if I use that binary classifier, I'm going to predict dog. I have a similar classifier, another classifier for cats. And I'm looking at that animal, I also get 80 or 90% probability to be a cat, because it's a foggy picture. I can't tell. I can tell it's an animal with 4 legs and no wings and stuff like that, but it sits inside the kitchen, but I can't tell if it's a dog or a cat. Both classifiers, dog and cat, will predict yes with 90% chance. But I know for sure there's only one animal in the picture, so predicting both dog and cat is guaranteed to be wrong. This is the most obvious dependency that can trick independent classifiers, when 2 things can be both predicted by the image, but obviously there's only one animal in there. Right? So again, I can't get into that, but there's a lot of area, including somebody in our lab is doing his PhD into multi-label problems. How do you approach those problems, and what is the idea? Now, it has to do with the combination of dependency and error, right? If I could train 20 independent classifiers, and they are 100% accurate, do I care about dependencies? No. If every single classifier will be extremely accurate, even though those labels are dependent to each other, meaning, having a cat is more likely to be in a house or next to a person or something like this. It won't matter if I have very accurate classifiers. So it's being recognized now by, I think, a guy from Poland who wrote the absolute best paper on the topic that said, look, it matters how accurate you are versus how much dependency you have. If you have no dependency, you can do everything independently. If you can be very accurate, you don't need to worry about the dependencies. But the problem is you cannot be very accurate and there are dependencies. So there's error versus dependency trade-off that you need to take care of those problems. And the models that work well don't scale well. That's another problem that in the industry people have. I can come up with a classifier that's quite good dealing with dependencies, but it's and fourth complexity. So if I move away from say 10,000 data points, not even that, 5,000, 10,000 data points, there's no way that algorithm is ever going to finish. Okay, moving on. What else we didn't do?
Missing data.
Missing data is an easy problem now. Missing it's easy, but there's something very related to data. Missing, you mean labels or not enough data. Let's say missing values. That's relatively easy. Missing not enough data. This question has to do with locality versus globality. Some classifiers are very local, like KNN, right? What KNN needs to give you a good prediction for a patient? What? What?
Decent similarity with other papers.
He needs some other patient or 2 or 3 similar to this one. Now it doesn't matter how much data you have in general. Whether you have 3 million patients or 30 patients, for KNN it only matters if you have another similar patient with this one, right? If you're lucky and you have a similar patient, KNN is going to give you the right answer. You may have 1 million patients but nothing similar with this one. Of course that's more unlikely, right? But still, it's a very local problem. Right? How about regression? Regression is not a local classifier. Regression is a global classifier. So to see this more visual, what happens if I have, say, this is my data space, and I have a bunch of pluses here in this corner, bunch of minuses here. Toyish example. And then I have a lot of minuses up to the diagonal. And a lot of pluses on the other side of the diagonal. I'm assuming this is very, very dense. So there's a lot of data here. What regression is going to do here? Probably regression is going to find this line. That's the best way to do it. Although clearly going to have these mistakes, assuming this is a negative side and these mistakes, right? But you can see how a regression in here cannot succeed unless I apply some kernel trick or some transformation or something. There is no line that can do this. What KNN is going to do here? It's going to do very well because KNN is a local thing. It will predict this point here based on the neighborhood. Assuming there's enough density, it won't matter what's the other thing. So KNN has advantages. KNN can emulate or KNN-like strategies. You can complicate KNN to make it very fancy. That can separate the data into many, many parts. Same thing with a decision tree. A decision tree, if you drill it deep enough, it's going to find separation. Even though this decision tree can only do vertical and horizontal, it's going to find separation lines, right? That's going to start looking very good if the tree is deep enough. A decision tree has the advantage that it doesn't need to make a model assumption about the data, same like KNN. It just does it locally, and those local regions can be in any shape or form or arrangement they want, as long as I have density. Now, KNN is not the same as a decision tree because decision trees can decide to say, if I limit the complexity of the tree, to say, okay, I'm going to sacrifice this part of the data here because I don't have enough leaves in my tree. Right? KNN never has that problem. KNN can always work locally, but local, I have to have densities. So what can happen is if I have a regression, like a lot of minuses, a lot of pluses, where KNN is going to fail terrible? KNN is going to fail in here. If this is a plus, just an out plus, KNN cannot predict this point properly because there's no locality, but regression can. Right? Regression, once it's aligned, it can do whatever. The problem in here is that if I'm on the right side with those pluses, regression can do them right. But if I have a minus, that's going to be a mistake. However, if that region has density, there's a lot of plus and a lot of minuses here. Now KNN wins again, right? Because if regression cannot do this, assuming there's a lot more data, force the line that way. But if there's pockets of locality, KNN starts working. So I'm not proposing here that you think of these issues theoretically. Let academics and scientists, PhD people do that, unless you want to be one of them. I'm asking you, go work for a hospital. They show you database of patients. What do? You have to consider issues like this. If you show me a patient that's of interest to you, talk to the doctor. The first thing you should worry is not how to approach machine learning, but rather how many patients like that are in your database or in the past. What are the important characteristics of the patient? Okay, blood pressure, I don't know, diagnosis code, age, maybe location, pollution, whatever. Put a query in that database. How many patients are coming from that area with that age, with that blood pressure, or with that blood pressure range? And if you see a lot of them, then means there is probably a pocket there. If you see very few of them, there's probably some isolated case. Okay? So I think this enough data. We're not talking theory. In theory, if you talk about joint distributions, you need an exponential number of data points in the features that you're never going to have that. But in more concrete terms of what to do, I think you should wonder how the data looks like. What else we didn't do related to missing data?
Skewed classes.
What?
Skewed classes.
Skewed classes? I'll get to that in a second. We do a lot of that in IR. In IR, when you ask Google for documents, how many good documents or relevant documents are there out of the web? Very few percentage-wise, right? So people who do ranking have solved that problem by saying, look, I can't really classify documents because if I say no good, I'm going to be right all the time. So instead of objectives like that, accuracy, they have a ranking objective. Question?
How do you know that you have enough data, or this much data is enough, or it is not enough, we need more?
Right, so I think you guys should be able to answer that question, not all the time, but how do we know we have enough data? What we look at. Again, enough data is an ill-formulated question or problem, because I may have very few data points and yet do classification perfectly. Right? Imagine a KNN that comes with always very well separated pockets, few pluses, few minuses, and I have a representation in my training set of each one of those groups. Even though they're not that many, I can classify everything perfectly. So what is enough data for what?
What if you, let's say you have cats, data that has cats. So,
Pictures.
Yeah, but then that data will be able to classify cats only. So not that way, but let's say you have a proper set of data points.
Images.
Let's say. How do you know that that data will properly fit your model?
So that's not so much an issue with the data, I think, the way you're asking, but rather an issue with labels. I may have a lot of images, but you saying I have only labeled cats in those images. And now my images might contain other things. Can I predict people, cars, rainy days, whatever it's in there to predict, if I don't have those labels? I mean, the typical supervised answer is not. You need those tags. In a multi-label setup, that could be a problem that some things is tagged a lot, like person is tagged in a lot of images, but something very specific, like say some particular dog, is not tagged that much. So out of 1 million images, the person balance, it's 40% of the images have person and 60% do not. But for a different label, like that particular dog, there's only 1% of the images who have that dog and 99% do not. Is that the question you're asking? So typically, data, it's easy to get by, but not the labels of the data, typically. Now, there are cases in which data itself is hard to get by. So medical data, for example. Very few hospitals and agencies, medical agencies, are willing to give that data. You have to, the worst is the Veteran Affairs Hospital in the United States. This is government hospital that deals with medical records for people who've been in the army. So they took the most draconian measures to make sure that their employees and other contractors cannot leak the data. Because those would be kind of the most sensitive data you have. It's not just medical data, it's medical data for people who, they have some problems due to the wars they fight in, so that's the last thing you want to have out. And there are draconian measures in place for this, but that makes it hard to get. So from a research perspective, the harder you make your data, the less available it is, the less people gonna have access and explore it and do something with it useful.
Is it that there's something like semi-supervised learning?
Right.
Stuff like when you have some data, some of the data have the label, while some don't have the label. So you might need use the data which have the label to generate a classifier and then try to leverage the unlabeled data. Is it something like semi-supervised learning?
Of course. Semi-supervised is not a hard topic to crack, as in boosting, you should go home and study it. It's an actual algorithm, implementation, engineering, all that. This is more like a story. It depends what you want to do. Right? Anybody can imagine, I have a training set, and I have an unlabeled set. And I have a test set or some need to predict something. So how can I use the unlabeled set? The ideas in semi-supervised learning are pretty straightforward. There's nothing, wow, terrible, hard to understand in there. So I could train a classifier on my training set, for example. Then what? Predict label for the unlabeled set. A naive person might say, okay, now that I have label for unlabeled set, make a bigger training set, right? Why not? If this is typically small, right? This is 10% of the data, let's say 5%. This is 90% of the data, and this is another 5% of the data. 100%. So if I get the labels for this set, it will be a much bigger training set, will solve a lot of data shortage problems, right? But of course, the labels I have here are the ones that I just predicted, so they just gonna reinforce the current classifier that I've trained. That classifier is gonna appear a lot better now, because instead of accuracy 70%, it's gonna have accuracy 97% now.
Well, maybe like we can extract features using unlabeled data, and then train whatever training, like classification.
So features, let's assume we have the features extracted everywhere. We'll not deal with the feature extraction part. So if there's images, we have the features. If they're text, we have the words, right?
I think the problem here is how to tell the quality that the quality of the label you generate for the unlabeled data. So how to.
So MES classifiers might give me not just the prediction, but the probability. a lot of classifiers, when they predict something, they say, I predict that probability or confidence 80%, right? Because most classifiers give a score, and a lot of the scores are passed to a sigmoid function of some kind, like in a logistic regression or in neural networks, right? And that score is transformed to a probability. The higher the score, the more probable that output is. But you should know that, I mean, we talked about that, that probability is fake. It's whatever comes out of the sigmoid. So now if the classifier chooses to multiply its score by 100, all scores, then everything that's going to come out of the sigmoid will be closer to 0 or 1, right? Look at the sigmoid. If my scores get pushed to the extremes, then the probability coming out will be closer to 1 or closer to 0. So that sigmoid cannot be a true probability for being correct. It's just a fake probability produced by a sigmoid function or a tangent function. But I can definitely use it as ranking. I know I'm more confident on that point than on that point because the score was higher. So I don't want to delve into this too much. One thing I can do that's intelligent is to do a cascade model to say, if I really want to do that, use those data points, I just take the most confident labels, not all of them, and I add those to the label set. So I only add 10% of the ones that are predicted labels, not true labels. I add those in here. I retrain my classifier. And now, what?
See whether it have improved performance on testing.
I need some sort of validation set or test set to see how things have changed. And if they have changed, I need to figure out the labels I added in help me or not help me. So validation set is necessary to measure what I've done. Assuming the test set is reserved for production purposes, like that, I can't really use the test set for training the algorithm. Test set is typically something that you can never touch. Only when you put your system in production that your method is going to work here. But a validation set is necessary. What else can I do?
Can we like run some kind of a clustering based on the class of the unlabeled data, and then somehow correlate the clusters to the classes that is we already have in the labeled data, and then pick up the most correlated data points?
So I clustered this data set, you say, the unlabeled set.
Based on the number of classes we see in the labeled data set.
Okay.
And then-
But clusters are what? Based on labels? Like 20 newsgroups will have 20 clusters because there are 20 labels?
Yeah.
Okay. So it's saying take the number of labels or categories and then create 20 clusters here. And then try to align these clusters to the labels somehow. That's hard because we don't have labels here.
No. So, but then you have features, right? You can see where the feature spaces align, and somehow the categories, the features of the category of the label set, and the features of the categories you have label set.
Oh, that's very creative. So yeah, you should try that over the summer. Let me know how it goes. So what he's saying is that if I have a bunch of clusters here, and obviously label categories already created here by the labels themselves, right? This is it's saying, look at the features. Can you correlate which one correlates with which one? And if something correlates a lot, this probably corresponds to that label, something like that. I don't know. Sounds interesting to look at.
So, as good as again, you are predicting the unlabeled set from the trained set. So you don't know if that
Well, the clustering, I think the way he meant, does not have, it's not predicted by the labels. It's like I think you can do some clustering where you influence it with your predictions too. But let me talk less speculatively about what actually is being done. The most useful part of an unlabeled set is to pick indeed more data points for my training set, to increase my training set, but not with predicted labels, with true labels. So the setup in which this is the most useful is to say, I already have 8% of the data labeled, and I have money to pay for another 5% labeling. That is, I'm hiring people, doctors or whatever, they're gonna look at these documents with human eyes and then create an annotation. Which 5% should I choose? That is the most useful thing that an unlabeled data set can do. If it's very vast, like a web nature, in which I can pick everything I want effectively, this is super big. And I have a very small budget, I can only label few things to improve my classifier. Which data points in here are the best to label to improve my classifier? So I have a classifier, a support vector machine, or boosting algorithm. I train it, I got a result, maybe checking the validations there. I can predict the labels for the unlabeled set if I want. And then I can pay somebody for very few of these documents or images to get part of my training set. I can pay for annotations, but which ones do I pick?
The most ambiguous ones.
Most ambiguous ones. So that's active learning. That's how it's called. Annotate or label ambiguous. Sometimes, 50% confidence. Those data points. There's a question. So there are many strategies. People in machine learning have looked quite a lot at which one of these data points are the best to help my classifier. In this sense, those ambiguous points will be where? They're unlabeled. I'm predicting labels for them, but where would they be? What makes them ambiguous? Is this here ambiguous? Or here? The farther away from this line, the more confidence I have that I can predict it right. So the ambiguous points are the ones that are, they're not labeled because I don't have their labels, right? But I know how close they are to the line. And if they're close to the line, I know that even if I predict something, I'll have little confidence because this point is so close to the line, could be either way. So now the idea is that if you label those, you gain much more information than if you label points far away. This in 2D, this looks like you could say, okay, labeling 2D points, how much this line doesn't have a lot of movement in 2D, doesn't have enough freedom, but in 300D or 300,000D, there's a lot of oscillation the plane has, so labeling points close to the plane typically helps. That is, if the plane is in a decent position to start with. This doesn't apply to a random line. If my initial classifier is random, picking points close to it doesn't necessarily help. But if this is a, say, 60-70% accuracy classifier, then it starts making sense to label it points close to it. So what happens in reality in active learning, the optimal distance from the line is judged not the closest possible, but is judged in conjunction with the confidence. What happens is, here's my current line, and here's my confidence. It's saying, effectively, non-rigorously speaking, I think the line is anywhere in here. This is the current one I have, but it might be a little there, a little there, a little there. So I don't want a point here labeled, necessarily, because that's too close based on my confidence. The best points are around here to be labeled. That whatever the line actually is, this point is gonna help. So this depends on classical classifier. We say, okay, this is a linear function. For linear regression function, this is quite easy, but for boosting algorithms or for support vector machines, this can be quite complicated. So another thing we didn't do in support vector machines, you can think of support vector machines, if you never heard of them, they still align. They create a line based on a different principle than regression. But their main advantage is that they create the line in a different space than the feature space. Typically when we plot this one of those two plots, this is the data space, and we say regression comes this way. SVMs, or support vector machines, create the same, but they first move the data from the original space into a new space. So what happens is my original space looks like this, so I can't do a line that does this properly. The actual classification is this, right? To get the pluses out of the minuses. SVMs look for a data transformation that move it from this space into a space where they are linearly separable. So typically they work in conjunction with this transformation that's called kernels. Now kernels can be applied for other things than SVM, but they do these kernels, move the data from one space, typically not linear, because the easiest classifiers are the linear ones. If lives in a linear space, we can just do regression in that space. But if clearly regression doesn't work, we can move the data in a new space where circles or bubbles become straight lines. The easiest transformation that you can see that happening is from a data point that's x1, x2. I create a data point x1, x2, and the product x1, x2. Now, because one feature now is a product of the other two, this is significantly different than the original space. You can see these two ways. Geometrically, things that were circles now can be lines. Algebraically, regression doesn't have this ability. No matter what coefficients you get, regressions will be what? Sum of W, I, Xi, right? Nothing in this regression form maps into x1 times x2. Regression cannot take two features and make a product out of them. It can only add up features with coefficients. So the product, or something like the square root x1, square root of x2, those are things that if they give you the good classification, if this would be a good feature, the regression cannot create this feature by just finding coefficients. But regression plus a transformation like this becomes a powerful concept. So kernels can be used for regression algorithms.
Just wanted to say, like, mapping it to another space, could I think that, like, try to add some new feature to the training data?
New features, but these are not new features in the sense of missing features. Like you can look at a document with plain words, like the actual document, and you can look at the features and say, wait a minute, the essential part of this document that talks about how important education is in Massachusetts, it's not in these features. This is just missing. This is not really missing. The information is there. The product x1 times x2, it's not a new piece of information in a philosophical sense, because the information is here. The problem is the regression algorithm. Regression cannot make use of x1 and x2 into the same way like creating a product. A different algorithm might, but not regression, right? So we're not really extracting a new piece of information from an image or a document that was just not there. We're saying what we need to do is the product of those two, and regression doesn't have the ability to do that.
So, I'm not that familiar with it's completely into the working of regression. So, regression is basically a curve fitting, right? Can we, if we use a higher order polynomial for fitting a curve, will that be able to actually do
Yes.
something like this?
If we use a higher order polynomial, effectively we can do x1, x2 if we fit a parabola or parabola, I mean, parabola only have x1 square in it. But if we allow my model to have x1 times x2, x1 squared times x2, and so on and so forth, higher order curves, right? So what he is saying there is a polynomial of a high order, maybe degree 5 or 6 or 7, that actually looks like this. That's absolutely true. Problem is with polynomials of high degree, as in even 2, let alone 3 or 4 and 5, is that they're absolutely impossible to fit. Okay? And we're talking about many dimensions. We're not talking about 2 or 3 dimensions, right? That's easy. Maybe in 2 or 3 dimensions, if we only have x1, x2, and x3, we talk a quadratic curve. What's a quadratic? Well, it's x1 squared, x2 squared, and x1, x2. That's the only quadratic terms I can have. But, and if I talk about cubic terms, it would be x1 cube, x2 cube, x1 square, x2, x1, x2 square, and But if I talk about 100,000 dimensions, I'm suddenly in the documents world now with unigram counts. Quite hard to do cubic terms in there, right? So what people do, they impose a kernel, a transformation. The transformation might be a polynomial transformation, although a lot of them are these Gaussian-based kernels. So that very, very typical kernel used for images, used for text, used for certain problems, right? And those are imposed to the beginning, like the algorithm doesn't search for those. You set in the beginning, transform the data with a polynomial kernel. And what the algorithm does, it finds the best parameters in that polynomial kernel. You specify the degree, but then the algorithm, say a support vector machine, has some control over the kernel. And the main work that has been put is into how do you do the optimization? How do you actually train, if you know you have a second degree polynomial kernel, how do you train an SVM with that kernel? Because now the objective is more complicated. So there's a lot of linear algebra that goes in that says, okay, here's how you do it. Okay, moving on. What else we did? Yes?
Is there a way to use a reverse GAN model?
A what? A reverse?
A reverse GAN model. Adversarial network.
Reverse? I don't know what it is.
I'm just saying, like, it's not a term actually, but like you can generate replicates of the original example using the data using a GAN, like an autoencoder, but you could also generate labels like this a while using that.
So you're not talking about kernels. You're talking about here.
Yeah.
Generate labels.
Yeah. Instead of generating the data.
The best approaches I know for this, including clustering and all that, requires a little bit of supervision. So most models I'm aware of are the ones that are saying, produce a candidate set somehow, but then I'm going to use minimum supervision to determine whether that's a good job or not. So a lot of things that I'll call, say, for example, relevance feedback. That means repeatedly add data points from here to training set. The ones that work really well are the ones that require a minimum of human feedback, even if it's implicit. Some of the best ways to collect feedback, like labels, if you don't have them, is to map them to what people already do. People click on websites, right? They don't say it's good or bad, but they click on the link. A link that's being clicked 1,000,000 times, it's better than one that's not clicked 1,000,000 times. So probably that document, that web page is better, right? So that doesn't cost nothing for Google to assign, to say this label has been clicked. It's probably better. We don't know for sure because we didn't ask specifically, is this document good or not, but we know people clicked on it a lot, right? CAPTCHA systems the same way, right? In order to pass a security question to get somewhere, you actually solving a labeling problem right there. People now track also the eyes of the user in front of the computer. I mean, with your permission, some do it without your permission, but mostly if I track your eyes or your mouse, maybe I can tell what's important in a document or in an image because I know where you're looking, right, at it. And if more people looked in the same spot, that's probably more important than the other spots.
So that is two-way street, right? If Google is producing 10 results, everyone will look in just the 10 results. They don't go to second or third page most of the time. People are probably to click on.
So actually Google is getting very good at this. Google does this per query, right? But they also cross the queries. If I put a query that's very similar to yours, they know our queries are very similar, both in terms of content and in terms of spatial, like we put them in the same day and we are in the same location. Because if we suddenly ask about Boston Marathon, on Monday, and we all from Boston, Google knows immediately there is some things related with a marathon, assuming some events are already scripted out, like a marathon is a big event, is scripted out, or a movie release or something. But if they don't know, they'll immediately, their system notice, hey, there's 2-3 million queries related to a marathon in Boston area, all happening right now. There's something going on. Because they cross all those queries. and they identify the keyword marathon, which is a very rare and very full of content keyword. And they all know the IPs of everybody is in Boston area. So they can do a lot of aggregates that way. Now, in terms of the actual list of results, you'll be surprised. You're right, most people only look at the top few things, and if they don't find what they look for, they just get out of that page or change the query. But out of 2 million people, quite a few will go to the second page or the third page. If I keep track of their sessions, if I know you, that's your IP, you put in this query, and then you immediately put another query, and immediately put another query, I get a pretty good sense of what you are looking for and how far down is in the list. The reason people put the second query almost all the time is that the first query did not produce the result they wanted. But they notice something that they need to adjust in their query. So Google is quite good at seeing who's going, how far, and the reason they can do this is because there's so many Google queries. Aggregates work much better if you have a lot of things to aggregate.
So you would not know if Google
So IR is not a problem. The biggest problem in IR is semantic meaning that's not explained word in words with keywords, factual, location, dates, names, and there is no good result. Everybody puts a question, even if there's 1 million people putting that question, no one finds the results because the keywords they use are not indicative of what they mean, and then there's nothing for them to learn from there. For that kind of query, they're always going to fail. But it's only when keywords don't match the content. And by now, people have learned that Google and Bing and everybody is better at those things. They just can't do it. Okay, moving on. Because there's quite a few things we did not do.
What about like time series data?
Yeah, that's another one we did not do. I want to talk a little about that. How much time do we have left? 20 minutes. So how about time, series, and sequences? What if my data really doesn't come in a standard feature format, right? Our data set so far have always been 1 to n data points and F1 to Fp features, right? And then every data point is an array of values or some categories, right? What if I have a patient? A patient might have an array of values, but 3 months later, the same patient has different values because I did more tests, right? And then again. There are 2 types of time series or sequence, but sequence it's a little different than time series. Sequence we actually did. I don't know if you remember the first time when I wanted to skip them, but then I put it in the homework and then I get back to them because I wanted you guys to do the homework. That thing with mining frequent item sets. Anybody remembers that homework one? Frequent item sets? A priori algorithm? Yeah. You can just change a name there and sets become sequences. Okay, and it's very straightforward to do that. But time series, it's a problem. Here's one question. Are patients, which clearly have a time series, right? A patient has certain phases of being sick and a lot of measurements. If this is the same patient X, but this is time 1, this is time T2, and then later on, it's the same patient X at time T3. That's an idea for a very natural time sequence. Definitely if you ask a doctor, some of you maybe know that, a lot of the things that happen with people that are not obvious things, you know, I broke my leg. That's not a sick time serious thing, the fact that somebody broke their leg in an accident. But a lot of diseases evolve with time. They have many phases, they have many symptoms. Very few things that matter in medicine are instant things, like, you know, I broke my leg. I mean, that happens, but that's easily fixable and there's no evolution for it. So that's patient. Another thing that's another good example is stock market. A stock, particular shares where you might buy, looks like what? Here's time, and here's the stock price. Anybody here investing into stock markets? Few people? We see a lot of these plots, right? So, are those the same kind of data and the same kind of problems? They both clearly have an evolution notion, right? You look at a stock, say Netflix stock. What happened with it? You are in the stock market, you want to decide buy or sell, typically. That's the main question. What should I do with this stock? And the other typical question is long-term versus short-term. It's something I want to do right now, or I'm planning for, I don't mind a little fluctuation if I'm planning a long-term investment. I care about the bigger trend. But if I want to make money right now, I care about what's going to happen tomorrow or next week. Right? For the record, I've always had a good intuition about stock market. That's what I say, and that's what everybody thinks. But I never have the courage to put any money in it. Only one time I thought I would invest, for real, but I never have any money. And that one time when I thought, maybe I said this already in class, the only one time in my life when I thought I would buy those shares is when I saw the Apple dude with the first iPhone in 2007. When I saw that phone in the pictures in the news, I thought to myself, with no economic background whatsoever, I didn't do economy or something, that thing is going to change the world. I would buy Apple stock. But that's the only time when I would have bought something if I had any money. Now I have students which are not economists, they do machine learning, and they made a lot of money by investing last year in NVIDIA, for example. The reason they figured that out is because you saw Chen in here. He figured out, hey, a lot of the AI is going to happen, and a lot of the AI goes through CUDA, and so NVIDIA is going to go up. So he put some money in NVIDIA, I think the stock tripled. Back to my question, are those the same kind of problem? Why not? They both depend on some evolution. And whatever we measure about patients probably is consistent, right? Like we can assume the columns are consistent. It's blood pressure, temperature, blah, blah, blah. Those are the same columns later on, right? I mean, we're not assuming here that medicine had a breakthrough and out of a sudden there's something going on new. Same thing in here. Whatever we measure about the stock, mean, variance, estimates, windows, they go back in the sliding window of the last 10 days window. The measurements are consistent, just at different points in time. I'm asking it, is this the same kind of problem or not? Yes.
I think that depends on a lot of factors. This is more defined than that.
Which one? This one depends on a lot of factors?
No, that is more defined, right? In terms of what the symptoms are, plus we most often always know what the outcome was, the label.
Right, I'm not saying the stock people only look at the stock fluctuation. Maybe they have other things to look at. Most people correlate the timeline in stock market with other events. They plot in here, for example, political events. This is Donald Trump tweets, everyone tweets something, boom, the stock market. This is political events. This is maybe weather events. So the typical stock market people now, they don't just look at the price of a stock or an index. They also have these aggregate indexes. But they look at, okay, we talk about oil. That's related to what? That may be related to the politics in Iraq or Iran, where the oil is. So these guys have an election. That election may influence the price of oil. I'm just making something up here, right? There's a lot of other things like development. If I change the law for immigration, for example, that's going to affect the tech sector because the tech sector uses a lot of guys like you to be employed. And if immigration is harder, Microsoft or Google may have to move to Canada or to China these are real concerns. This is not just the stock price, but other things that are happening. So there could be other factors here.
So what are we actually predicting in patients for each?
Maybe we predict a certain treatment or a certain outcome of that disease. You know, it's how is he gonna die? Is he gonna need a transplant? Is he gonna come back to the hospital? Actually, that's a big problem for hospitals. If you solve that problem, you'll be a millionaire. Tell them which patients are coming back and when. They would love to. I'm not kidding. For a hospital, one of the biggest expense is to figure out who's coming back and whether it's tomorrow or next week or next year. And that's because the laws are set up in many states, including Massachusetts, that a hospital cannot refuse patients. So you could say that makes sense from a human perspective, but from a managerial business perspective, they know what patients are the ones that requires a lot of attention and no money because they don't have proper insurance, So they would love to know when those people are likely to come back. They go as far as even monitoring those people to say, if you don't take your medicine, we're not gonna take you back, right? Because they're really afraid if people don't take their medicine, this happens all the time, and they went as far as sending people to their homes to make sure they take the medicine, or putting those devices that if you take the medicine, the device beeps and says, this guy took his pill. Back to this problem, why are those different? Or why not?
It's way more volatile in the stock market.
That's one thing. This is far more volatile in general, even for long-term stocks, than this.
But then again, there could be a common thing about the outlier detections. Like in medical history, if 98% of the cases are the same, I don't want to check them. I want that 2% which display some outliers, and similarly in stocks, if there's some outlier, I'm way more concerned about that. If so, everything is going normal, it's fine. But if there's some outlier, I want to see that first.
So I think he said two things at least. One thing here is that predictability of patient evolution is much easier, much more consistent. If people start having diabetes, after a while, doctors will predict with very high accuracy how the diabetes is gonna go. Because if you live in a certain environment and if you have a certain diet and if you humans are very consistent that once you develop some disease, how is that going to go? Because we all have the same hearts and lungs and stomach and all that. There's magically somebody healing his diabetes by not doing nothing? Impossible. So there's no volatility. The volatility here comes from the patient, whether he takes his pills or not, whether he decides to change his diet or not. But we can measure those things more accurately. I think that's what he said. Problem with stock market is that the biggest changes in stock market don't come from consistent reasons. Consistently, yes, we can predict certain trends. But from an investor perspective, if every once in a while something major happens and drops the stock or increase the stock a lot, something like in the extreme would be a terrorist attack or something like that, those have more influence for the stock market than the consistent reasons, like interest rates. Those are well planned, and pretty much the interest rates are changing based on employment, trade, and so on and so forth. Could be predicted perhaps in machine learning sense quite consistently. But the biggest changing in stock market come from things that are hard to predict. And that's why in here, sometimes there's machine learning algorithms that do this. They have to shut them down in certain events because they don't want the machine learning to take over the trade if something like a terrorist attack happens. So volatility is one thing. How about the actual delta from time to time? Is a disease evolving? If I look at delta, say I measure something every day, take the day as a unit. There's a difference from here to here, right? So I can measure that difference in blood pressure, in, temperature, whatever deltas I measure, I can say, take the deltas interval as 1 unit, 1 day. So I measure something every day. How is this evolution? This is delta from day 1 to day 2. This is delta from day 2 to day 3. This is delta from day 3 to day 4, so on and so forth. Maybe this is a week, not a day. And this I can do the same, right? I split this into the same thing. This is 1 to 2, 2 to 3, 3 to 4, 4 to 5. So I'm looking at how much things have changed from today to the next time I do the measurement. I'm assuming consistent intervals, like every day or every week. Are patients the same as stocks in that delta sense? No. Because the things that I measure here, they don't change the same way per interval, right? If I know I'm in day 17 of a disease, or week 17, or year 17, and the stage of the disease, that's not the same. This is much more consistent per delta intervals. In other words, if I'm here, even though this stock had a certain evolution in the past, I may decide the only thing matters to me is what happened here in this past few days. In fact, a lot of trading is done like this. I'm only evaluating the past week or the past month. It doesn't matter to me that Dell computers were about to be bankrupt 3 years ago. Actually not, when they're about to be bankrupt. A few years ago, Dell was in trouble. Few more years ago, Apple was about to be bankrupt, right? Does that matter today for the Apple shares that 10 years ago they will have financial difficulties? Not at all. Nobody's trading Apple stocks now based on what happened in 1996.
What if every year, whenever they release a report, their stock falls down and eventually it comes up in 2 days, then there will be this pattern that matches.
Right.
Then in that case, then all
But
days
that's
have
one of these very small things, right? So that's only matter if you're very speculative, you want to make money by tomorrow. Most people know by now that whenever there's something, a little bubble, it's not, I mean, I'm not an investor trading like person, so I'm not an expert at this, but my guess is that people care very little about these one-day bubbles. They care more about at least say a month or 2 months, if not further. And plus those events are well known. Every time Apple has one of these keynotes now, they know the stock is going to go up a little bit and then down. People have learned what to correlate with the stock. My point is, in stock market, you don't really need that much history. The last few things were absolutely critical, as opposed to here, where clearly what happens here cannot be independent in a disease sense from what happened earlier. A disease always progresses from little stages to big stages, while a stock market, a stock can go up and down in any direction, and it's pretty much irrelevant what the company did 20 years ago. In patients, that's never the case. What happened 20 years ago very likely going to affect what's happening now with the patient. So the book, I had some slides here about these two problems, the sequences and stuff, but I don't think we have time for those. The book talks about the Agrawal book, the ones we've been using a little bit for this class, talks about how to manipulate time series and how to manipulate sequences. But that's not enough for you to actually solve one of these problems. So I looked at the book and I've read a few pages there. I don't think that's enough to deal with these things properly. So I think the right thing is, if you're to do this, I think it requires a specialization like deep learning sort of specialization. If you were to do deep learning, sure, you learn about neural networks and you learn about TensorFlow. You actually need a course into deep learning to go work for Facebook to do deep learning. I think the same thing happens here. If you want to be working with patients' data or with stock data, you need a much more fundamental approach and training into how to deal with sequences. Time series, sorry, that's what we said, time series so far. In terms of time series, there is one more thing that matters a lot. I guess that's for sequences too, but something that a lot of people have been worried. Anomalies, which I want to point out, those are different than, what did we call them in here? Outliers, right? Let me just say here, not outliers. So outliers, that's another thing that we didn't talk that much about. How do you deal in certain, say, supervised learning models. Those are again the most used one. How do you deal with outliers? For example, ensemble methods are very bad, some of them, because they focus a lot on the outliers. And if those outliers happen to be annotation mistakes, which is quite common if you have annotation mistakes, the outliers will be the one that is the farthest away but the wrong side. Then the boosting algorithm will focus on that outlier. It's exactly what you don't want to do. But the most important thing here that we didn't talk about is noise. Noise is a huge area of machine learning. How do I deal with the fact that both features and labels have a certain chance to be wrong? Because I measure blood pressure, I measure it wrong. That's a feature being wrong. I put a tag on a document, and the tag, even by the editor, the guy who's hired to do that, he put the wrong tag. Sometimes the tags are very similar. Health versus healthcare. And now you can put either one of them, but from a machine learning perspective, those are different tags. So this is a big deal in reality, because in practice, data is much more noisy than those academic data sets, which, by the way, are noisy too. The reason you didn't do so well in 20 news groups is because some of those labels are wrong. But in practice, there's much more noise than in academic data sets. So it's essential in a production system to be at least aware of how much noise you have. A lot of the consulting I do these days is just explaining medical people that they have too much noise in their data for the kind of algorithms they want to run. Now, anomalies in a sequence are not really outliers. So I think maybe some people try to come in, right? What's an anomaly? I see this graph here, and out of a sudden something happens, and out of a sudden something happens this way. That's where people become billionaires or they lose everything they have. Right? In these systems, anomalies are a huge deal for stocks. In this system, the only anomalies I'm aware of in medical systems is where they perform the wrong procedure on the wrong person. They had few patients in a hospital, they had to do something like a surgery, and they did it on the wrong person. Yeah, I wouldn't worry too much about that. That's not happening consistently, but anomalies are a big deal in the stock market. With that, I think we're done. We have office hours, of course. That's going to happen for me at least today and Friday.